Hello everyone, this is Sebastiano Stipa and this is the third video tutorial of the dynamic mesh series in OpenFOAM. In the first video we saw how to set up and run an advanced block mesh. Then we saw how to use the interpolating solid body motion solver for moving the mesh around pitching airfoil. And in this video we will see how to use the finite volume motion solvers. The finite volume motion solvers are different from the mesh motion solver we saw in the last video because they solve a motion equation in order to calculate the point motion. In the previous video we basically did an interpolation of the motion of the body throughout the entire mesh, and in some sense all the motion solvers defined inside the SRC dynamic mesh motion solvers do this. They do not solve an equation in order to calculate the mesh motion. This kind of motion solvers can be found inside the FV motion solver directory, and basically there are displacement motion solvers and velocity motion solvers. For the velocity there is only the Laplacian motion solver, and for the displacement there is the SBRStress and the Laplacian motion solver. The Laplacian motion solver solves for the Laplace equation for the motion displacement, for the point displacement, while the SBRStress is more, let's say, is more reliable since it uses a different approach. It solves still an equation, but is the solid body rotation equation for the motion displacement, which comes from the constitutive law for the materials. If we used only the constitutive law of the materials, the solid body rotation are not allowed. So we had this term which accounts for the solid body rotation of the body. You can find this source code here, and basically this is the equation which is being solved by OpenFOAM. So you'll have these two extra terms with respect to the Laplace equation, which is only this one, which is this term, and this is the solid body rotation term due to Dwight in 2004. So you have also for the Laplacian solver the component where you can, if you want to restrict the motion to one direction, you can use the component displacement, but the working principle is really the same with respect to the full displacement or full velocity motion solver. Okay, let's go to the control dict of the case. The case is the same with respect to the last tutorial. The only thing that changed is the fact that we have to add a new field which must be solved for, which is the point displacement, and you can find it in the initial condition and boundary condition directory, the zero directory. So here you will see that there is this new field, and you have to provide boundary condition and initial condition for it. So the initial condition is 0 everywhere, and you see that the motion of the body does not enter anymore the problem inside the dynamic mesh dict, which is where it is not specified, but it enters instead through the boundary condition for the point displacement. Here we specify the motion of the airfoil, which is a type angular oscillating displacement. We specify the axis, the origin, which is 0, so we are making the airfoil oscillate with respect to the leading edge, the angle zero, which is a useful property if you want to start if the starting configuration is not the zero amplitude configuration. Like if you want to do a pitch only in the let's say in the negative for the negative angles, you have to start not from 0 but from 3.14, which is pi. So you have to put 7.5, which is the half of the amplitude of the oscillation. And then the airfoil will not oscillate around the initial condition, but will perform an oscillation around 7.5 degree pitch. Then you have to specify the amplitude of the oscillation in radians. So here I use the calc option. Then you have to specify the omega, the angular velocity, the pulsation of the oscillation in radian per seconds. Here is 6.28, which is the same of the last video, meaning that the airfoil is performing a complete oscillation in 1 second. And then you have to specify the initial value for the motion at this boundary. Then you have the same empty for the front and back patches, and then for the rest of the patches which are accessed with the wildcard, which is the star symbol, you have fixed value, because the inlet patch and the outlet patch are not moving, they are fixed. Okay, so this is the point displacement file. Then you have the dynamic mesh dict, which until here is the same with respect to the last video, but this time we change the solver, which is this displacementSBRStress, and we choose a diffusivity, which is this parameter here, gamma. There are different methods for choosing the diffusivity. We will see the implication of the most important one during this tutorial. So for now we use an inverse distance, which means that the diffusivity is calculated, let's say the distance from the moving patch is calculated, or from the patch which is specified here is calculated, and then diffusivity is the reciprocal, is inversely proportional to this distance. Okay, so the last thing that we have to set is, sorry, I opened this. The last thing that we have to set is the way we want to solve for the point displacement. Here in the FV solution we have to specify it. So the field cell displacement must be present in the solver subdictionary, and we have to specify the solver which we are using to solve for the point displacement, the smoother, the tolerance, and the relative tolerance. So I use the geometric algebraic multigrid here, because it's very good for let's say laptops, because it's very fast if not massively parallelized, and I use the Gauss-Seidel as a smoother. Okay, so we are ready to start the simulation. The rest of the case is the same with respect to the last video. You will find this case, a link for this case into the comments of this video. And yes, here you can see that there is an all-run bash script that you can launch in order to run all the case at one shot. But here in this video we will go step by step. So let's enter the directory. Okay, let's load the OpenFOAM 8 environment variables. Let's launch the block mesh, then the extrude mesh, then we decompose the case, but before decomposing the case we have to copy the 0 point origin, renaming it 0 directory, because OpenFOAM only reads 0. For OpenFOAM, if this is called 0 point origin, it doesn't exist basically. So now we can decompose the case, and then we'll start the simulation. So we go for mpi run np4 PimpleFOAM parallel. Okay, now I stop this case because I already solved it. Okay, let me stop it from the background processes. Okay, so after the case has finished, we have to reconstruct the case with reconstruct par, and then if we want, or we can load the paraview, we can load paraview with paraFOAM, or we can transform in VTK, typing FOAM to VTK, and then a VTK folder will be created just like this one, and then we can just run paraview and read from that folder. So which is this one now? Okay, it is this one. Okay, so okay, this is the solid body rotating motion solver. You can see that here there is this subtle problem, which is that the inverse distance gives problem when computing the distance, let's say the diffusivity of this point, because it is not a smooth zone of the profile, so the diffusivity in this point is not well calculated. How can we solve this problem? Because if we had a finer mesh, this for sure would give us errors. So we have to adjust this problem, the problem of having this bad deformation here. In this regard, the solver that I explained in my last tutorial is better from this point of view, because you can fix a zone around the profile where the points are moving rigidly. But when we use finite volume motion solver, we have the possibility to use manipulators, and we have also the possibility to change the computation of the diffusivity. For instance, this is a trick that I always use. It is called the banana trick. You put here casually type the word like banana, and then launch OpenFOAM, and OpenFOAM will say, I didn't find this kind of diffusivity. The possible diffusivities are these ones. So the diffusivity that is more robust, of course, is the inverse distance, but in this case, for the airfoil, we could use the inverse point distance, which computes the diffusivity based upon point distance and not patch distance. Or we can also use the inverse volume, which is not bad. Talking about manipulators, the manipulators are the exponential manipulator and the quadratic manipulators. So now we are going to try the inverse point distance and the quadratic manipulator. In order to use the manipulator, you have to specify a method of calculation for the diffusivity and then put the manipulator in front of it, just like this one. So you specify the inverse point distance with respect to the airfoil and then put the manipulator in front of the of these two words. So the manipulator will take the computed diffusivity field and manipulate it in some way. For example, let's open the exponential manipulator. Okay, so it returns the exponential of minus alpha divided for d, where d is the diffusivity. Alpha must be specified after the exponential word, just like this. Exponential 30, inverse point distance, airfoil. Instead, the quadratic doesn't need a number after it, so this returns the square of the given diffusivity, so it doesn't need any number, any additional number. So let's see with this kind of diffusivity, quadratic inverse point distance, here I have already solved the case, so I'll open it in ParaView. So this seems a lot better. As you can see, the point is correctly moved, the point at the trailing edge. So with this kind of mesh motion solver, you have to really tune the parameters of the mesh motion. Every problem has its own parameters and you have to make a lot of attempts before obtaining a good mesh resolution throughout the iteration. But with some effort it's possible to do it. Okay, so now let's see very quickly how the Laplacian finite volume motion solver works. The case is basically the same with respect to displacementSBRStress. The only thing that changed is the presence, is the difference, is a different solver. So this one, you have to put displacementLaplacian instead of displacementSBRStress. For the rest is the same. So here, just to compare, I used the same diffusivity with respect to the latest simulation I showed you, in order to show you the differences between the Laplacian and the SBR-stress equation. So let's reopen PeerView. As you can see here, the presence of these bad quality cells is not eliminated. So for me, the SBR stress is better for this application, but it could happen that the Laplacian is better for other applications. It's true that in this case, this setup is the best. In this case, this setup is the best because it gives a high quality mesh throughout all the iterations. So in the next video, I will show you how to run, how to use the solid body rotation with the arbitrary mesh interface, which is this one. And if you have particular requests for different motion solvers, please ask in the comments. So this is another approach, another more approach, which instead of deforming the mesh or with an equation, or instead of deforming the mesh with an interpolation of the motion of the body throughout the whole mesh, is directly splitting the mesh into a region which is fixed and a region which is rigidly moving. So thank you for the attention, and see you in the next video.